When 3I, Atlas, crossed into our solar system, astronomers thought they understood what they were seeing. Another interstellar comet, nothing more. But something was wrong from the start. The object's trajectory didn't follow the chaotic path expected from natural visitors. Instead, it traced a series of precise arcs, threading between planets with timing so exact it defied probability. Then came the jet's razor-straight columns of material that refused to spiral as physics demanded. And beneath all of this, a pattern emerged in the data, one that researchers initially dismissed as noise. 3I, Atlas, wasn't just passing through, it was scanning. Every close approach to a planet triggered a burst of activity. Every orbit adjustment pointed instruments at critical infrastructure. The trajectory wasn't random, it was methodical. What astronomers first labelled as gravitational chaos now appears to be something far more deliberate, a systematic survey of our solar system, executed with precision no natural object should possess. The geometry problem, the trajectory of 3I Atlas, violates fundamental expectations for interstellar objects. Standard gravitational models predict that visitors from beyond our solar system should follow hyperbolic paths, sweeping in from the void, bending around the sun, and departing without significant deviation. Oumuamua and Borisov both adhered to this pattern, their orbits tracing smooth curves dictated by solar gravity alone. 3I, Atlas, breaks this rule systematically. Orbital reconstruction teams at the European Space Agency's Near-Earth Object Coordination Center processed positional data spanning several months and found something unprecedented. The object's path contains multiple inflection points, where its velocity vector shifts in ways that cannot be explained by gravitational encounters alone. Each shift is small, typically less than a few meters per second, but the cumulative effect produces a trajectory that weaves between planetary orbits with improbable precision. Dynamical astronomers use a metric called the Tisserand parameter to classify objects and determine whether their orbits result from gravitational interactions or require additional forces. For typical interstellar visitors, this parameter remains constant throughout their passage. 3I Atlas shows variations in its Tisserand parameter that correlate with planetary encounters, suggesting active trajectory modification. The shifts occur at intervals matching its 16-hour rotation period, implying that whatever mechanism is at work is tied to the object's spin. Statistical analysis of the trajectory by teams at the Jet Propulsion Laboratory calculated the probability of achieving such a path through gravity alone. The result fell below 1 in 10,000, even when accounting for uncertainties in solar system mass distribution and perturbations from minor bodies. The most striking aspect is the object's perihelion timing. 3I, Atlas, reached its closest approach to the Sun exactly 8 days after solar conjunction, a window that kept it hidden from ground-based telescopes during critical observation periods. This timing placed the object in an ideal position to observe inner planetary dynamics while remaining difficult to track from Earth. Trajectory analysts noted that shifting perihelion by even 2 days in either direction would have exposed 3I, Atlas, to comprehensive monitoring from major observatories. The precision required to achieve this timing through natural processes alone strains credibility. Gravitational slingshot maneuvers, the standard explanation for trajectory modifications in natural bodies, require close encounters with massive objects. Yet 3I, Atlas, maintained distances from Jupiter and Saturn that were too large for significant gravitational deflection, while still showing velocity changes consistent with active maneuvering. Radar observations from Arecibo's successor facilities attempted to measure rotation state changes that might explain the trajectory anomalies. The data revealed something unexpected. The object's spin axis orientation shifted by approximately 3 degrees between measurements taken weeks apart. In typical comets, spin axis precession occurs over years, driven by asymmetric outgassing. The rapid precession seen in 3I, Atlas, suggests deliberate reorientation rather than passive response to internal pressure. Independent confirmation came from photometric monitoring campaigns conducted by amateur networks across 3 continents. Light curve analysis showed periodic brightness variations consistent with a tumbling body, but the tumbling pattern itself evolved in ways that matched predictions for controlled angular momentum modification. The rotation period held steady at 16.16 hours, but the orientation of the rotation axis relative to the Sun changed in discrete steps rather than smooth precession. Computational models attempting to reproduce the observed trajectory through natural means require fine-tuning of initial conditions to implausible precision. Teams at the Institute for Celestial Mechanics and Ephemeris Calculation ran Monte Carlo simulations with thousands of randomly generated initial states for interstellar objects entering the solar system. None produced paths resembling 3I, Atlas, without introducing non-gravitational accelerations. The accelerations needed are small, comparable to radiation pressure from sunlight, but their direction and timing show patterns inconsistent with simple comet outgassing. Standard comet jets produce force vectors that average to near zero over multiple rotations. The accelerations inferred for 3I, Atlas, show directional bias that persists across observation windows, suggesting selective activation of thrust mechanisms rather than symmetric sublimation of volatiles. This geometric precision extends beyond trajectory to the object's relationship with planetary orbits. Analysis of close approach distances reveals that 3I, Atlas, passed within optimal ranges for gravitational study of Mars, Venus, and Earth's moon, each time maintaining separation sufficient to avoid significant orbital deflection while maximizing observational opportunity for those bodies. Scan pattern recognition. The spatial distribution of 3I, Atlas's jet activity, reveals a pattern that defies expectations for random cometary outgassing. Between late September and mid-November, ground-based observers documented 14 distinct episodes of enhanced emission, each lasting between 4 and 12 hours. Standard models predict that comet activity should correlate primarily with solar heating, producing jets that activate when surface regions rotate into sunlight. The observed pattern for 3I, Atlas, shows no such correlation. Teams at the Lowell Observatory compiled timing data for each outburst and cross-referenced it with the object's position relative to major planets. 7 of the 14 events occurred when 3I, Atlas's trajectory, brought it into alignment with specific solar system bodies, regardless of solar illumination angle. The first recognized pattern emerged during the object's approach to Mars. On a date in late September, as 3I, Atlas, closed to within 19 million miles of the red planet. Instruments aboard the Mars Reconnaissance Orbiter detected a sudden surge in hydrogen Lyman alpha emission from the comet's envelope. The brightening lasted exactly 9 hours before returning to baseline levels. Photometric monitoring from Earth showed simultaneous brightening in visible wavelengths, confirming genuine increase in activity rather than instrumental artifact. The timing aligned precisely with the period when Mars occupied the narrowest cone angle relative to 3I, Atlas's spin axis. Similar events repeated as the object encountered other planetary targets. Each episode of enhanced activity coincided with geometric configurations that placed specific bodies within a narrow field of view determined by the comet's rotation state. Spectroscopic analysis during these events revealed compositional changes in the emitted material. Baseline outgassing showed the unusual nickel-rich signature documented in earlier observations. But during planetary alignment episodes, emission lines from ionized calcium and sodium intensified by factors of 3 to 5. These elements originate from deeper layers within the nucleus, suggesting that the enhanced activity involved more than surface sublimation. The emission spectrum during alignment events also showed Doppler shifts indicating directed outflow velocities up to 600 meters per second, 50% faster than typical background emission. Statistical analysis by researchers at the Planetary Science Institute calculated the probability that 14 outbursts would randomly coincide with planetary alignments. The resulting p-value fell below 0.003, indicating high confidence that the correlation is not coincidental. Infrared monitoring from the Spitzer Space Telescope's successor instruments added another dimension to the pattern. Thermal emission from 3I, Atlas, showed periodic spikes in the 10 to 20 micron wavelength range, consistent with localized heating events on the nucleus surface. These thermal signatures appeared in sequences, with individual hotspots activating in rotation around the spin axis. The spacing between activation points suggested 8 to 12 discrete source regions distributed across the nucleus. Thermal models attempting to explain the heating through solar illumination alone required surface compositions with wildly varying albedo and thermal inertia, far beyond the range observed in any known solar system body. The most compelling evidence came from polarimetric observations conducted by teams using the William Herschel telescope. Polarization measurements reveal information about the size, distribution, and composition of dust particles in a comet's coma. Standard comet dust shows polarization patterns that remain relatively constant as the object rotates. 3I, Atlas, exhibited polarization variations synchronized with its rotation period, indicating that different surface regions produced dust with distinctly different properties. During planetary alignment events, the polarization signature shifted toward values typical of fine particles less than 1 micron in diameter, suggesting selective emission of processed material. This size distribution is difficult to achieve through natural sublimation, which typically produces a continuous range of particle sizes from nanometers to centimeters. Radio observations at millimeter wavelengths detected another pattern in the data. The Very Large Array monitored 3I, Atlas, over multiple rotation cycles, measuring emission from carbon monoxide and hydrogen cyanide molecules in the coma. The intensity of these molecular lines varied not just with rotation, but with viewing geometry relative to nearby planets. When Earth lay along the same line of sight as Mars, beyond 3I, Atlas, carbon monoxide emission intensified by measurable amounts. Similar enhancements occurred for other planetary configurations. The effect is subtle, requiring careful baseline subtraction and calibration, but multiple observation runs confirmed its reality. The physical mechanism behind this correlation remains unexplained by standard comet models, which predict molecular emission rates determined solely by nucleus temperature and composition, not by the position of distant bodies in the background. Magnetic field anomalies. Measurements of the magnetic environment surrounding 3I, Atlas, reveal structures that do not conform to expectations for cometary plasma interactions. When solar wind particles encounter a comet's neutral gas envelope, they should create a draped magnetic field configuration, smooth, bow-shaped field lines that wrap around the obstacle and gradually reconnect downstream. MAVEN's magnetometer designed to study Mars's magnetic environment, captured multiple passes through 3I, Atlas's extended hydrogen cloud. The data show field geometries that are anything but smooth. Instead of gradual draping, the magnetic field exhibits sharp discontinuities at specific distances from the nucleus, forming boundaries that resemble the magnetopause structures around planetary magnetospheres, rather than the diffuse interaction regions typical of comets. The boundaries maintain consistent positions relative to the nucleus despite variations in solar wind pressure. Typical comet magnetic structures expand and contract dynamically as the solar wind buffets them, with standoff distances varying by factors of 2 or more over timescales of hours. The structures around 3I, Atlas, remain locked at approximately 15,000 and 33,000 kilometers from the nucleus, matching the inner and outer extent of the hydrogen envelope mapped by ultraviolet observations. This stability suggests the boundaries are controlled by properties of the nucleus itself rather than by external solar wind conditions alone. Magnetic field strength measurements within these boundaries show another peculiarity. The field magnitude drops below expected values, creating regions of magnetic depletion reminiscent of diamagnetic cavities observed around some solar system comets, but far more pronounced and stable. Spacecraft carrying fluxgate magnetometers recorded field direction changes as they passed through 3I, Atlas's environment. The field vectors rotated in a pattern synchronized with the nucleus's 16-hour rotation period, indicating that whatever generates these magnetic structures co-rotates with the body itself. Natural comets can produce rotating magnetic field patterns through asymmetric outgassing, creating rotating plasma structures, but the rotation signature should blur out at distances beyond a few thousand kilometers where solar wind dominates. The structures around 3I, Atlas, maintain coherent rotation out to the outer boundary of the hydrogen envelope, requiring a mechanism capable of imposing organization over unprecedented spatial scales. Plasma wave instruments detected electromagnetic emissions from the 3I Atlas environment across a broad frequency range from a few hertz to several kilohertz. The spectrum shows discrete peaks at frequencies that are integer multiples of the rotation frequency harmonics that suggest a fundamental oscillation driven by the spinning nucleus. Similar harmonic structures appear in plasma wave data from Jupiter's magnetosphere, where they result from resonant interactions between rotating magnetic fields and trapped plasma populations. Observing such features around a comet is unprecedented. The power levels of these emissions exceed predictions from standard plasma physics models by 2 orders of magnitude, requiring energy sources beyond simple solar wind interaction. Cross-correlation analysis between magnetic field measurements and optical observations revealed another pattern. Brightening events in the visible coma coincided with sudden compressions of the magnetic boundary, as if pulses of material from the nucleus were pushing against the surrounding field. But the timing showed that field compression preceded optical brightening by approximately 20 minutes, the time required for material to travel from the nucleus to the inner magnetic boundary at typical outflow speeds. This reversal of cause and effect suggests that magnetic activity near the nucleus triggers material release rather than released material, modifying the magnetic environment, inverting the standard understanding of comet physics. Ground-based magnetometer networks detected ultra-low frequency pulsations in Earth's magnetosphere that correlated with 3I, Atlas's activity cycles. These pulsations, with periods ranging from 5 to 15 minutes, appeared during intervals when the comet's magnetic structures were oriented favorably relative to the interplanetary field connecting to Earth. The correlation implies that 3I, Atlas, generates field-aligned currents, or Alfvén waves, capable of propagating across interplanetary space and coupling into Earth's magnetosphere, a phenomenon never documented for comets, but common in studies of planetary magnetospheres and solar activity. The rotation paradox. Every attempt to model 3I, Atlas's rotation state, encounters contradictions that deepen rather than resolve. The photometric data clearly establishes a period of 16.16 hours. Multiple independent observation campaigns across different hemispheres confirm this number with uncertainty below 0.05 hours. But the implications of this rotation period conflict with nearly every other measured property of the object. For a body several kilometers across, spinning with this period, centrifugal acceleration at the equator reaches approximately 1/10 the surface gravity for typical cometary densities. This is manageable for consolidated rocky material, but approaches critical values for loosely bound aggregates. Standard models of comet structure invoke low-density rubble pile configurations, where self-gravity barely exceeds cohesive strength. A rapidly spinning rubble pile should shed material continuously, producing a diffuse cloud of debris. 3I Atlas shows no evidence for such mass loss. Imaging data reveal a compact, stable nucleus with well-defined boundaries. The contradiction intensifies when considering the object's jets. The straight-line geometry of these features requires that their source regions maintain fixed orientation in space as material streams outward for weeks. With a 16-hour rotation period, each source region completes over 40 full rotations during the time material travels from the nucleus to the observed jet endpoints. Elementary physics predicts this should produce spiral patterns, not straight lines. Attempts to explain the geometry through jets originating at rotational poles fail because multiple jets appear at angles far from any possible pole position. Models invoking rapid particle acceleration to speeds that outrun rotational smearing require energy sources orders of magnitude beyond available solar illumination. The numbers simply do not work for passive solar heating. Light curve analysis reveals additional rotational puzzles. The brightness variations consistent with the 16.16-hour period show amplitude changes over longer timescales that indicate precession of the rotation axis. But the precession rate is wrong. It occurs approximately 100 times faster than predictions for a comet-like body undergoing torque from asymmetric outgassing. The required torque levels would demand gas production rates that should be easily visible in spectroscopic monitoring, yet observed production rates fall short by more than an order of magnitude. Something is causing rapid reorientation of the spin axis without producing corresponding increases in detectable outgassing. This disconnect between rotational dynamics and mass loss challenges fundamental conservation principles. Radar observations attempted to measure surface properties that might explain the rotation paradox. Echoes from 3I Atlas showed unusual characteristics. The radar cross-section varied by factors of 3 across the rotation period, indicating extreme surface roughness or composition variations. But the polarization ratio of return signals suggested smooth surfaces at centimeter scales, contradicting the roughness interpretation. Attempts to reconcile these observations invoked layered structures with radar reflective coatings, but no natural process produces the required surface properties in objects with cometary origins. The rotation period itself shows subtle variations at the level of a few minutes across observation windows spanning months. These changes correlate with the object's heliocentric distance, in ways that imply external torques rather than internal mass redistribution. The direction of spin rate changes indicates acceleration during approach to perihelion and deceleration afterward, opposite to expectations for outgassing-driven spin-up. Theoretical models exploring possible rotation states rapidly exhaust natural explanations. A perfectly spherical nucleus could maintain stable rotation, but observations clearly show an elongated or irregular shape. An elongated body in pure rotation around its shortest axis would be stable, but the light curve's double peak structure indicates tumbling motion with significant energy in non-principal axis rotation. Such tumbling should damp out over timescales of months to years through internal friction, yet 3I, Atlas, shows no evidence for damping. Energy must be actively supplied to maintain the observed rotational state, but identifying the source remains problematic. Solar radiation torques are too weak, and outgassing torques produce the wrong temporal pattern. Thermal emission profile. Infrared observations of 3I, Atlas, reveal a thermal signature that defies straightforward interpretation. When sunlight heats a comet nucleus, the surface temperature should follow predictable patterns determined by solar flux, albedo, thermal inertia, and rotation rate. Teams using the James Webb Space Telescope's mid-infrared instruments measured thermal emission across multiple wavelength bands, building detailed temperature maps of the nucleus. The results show temperature variations across the surface that are far more extreme than standard models predict. Peak temperatures in sunlit regions reach approximately 320 Kelvin, consistent with dark, rapidly rotating surfaces. But adjacent regions show temperatures below 200 Kelvin, implying either extremely high reflectivity or active cooling mechanisms. The temperature contrasts persist across rotation cycles, indicating stable surface properties rather than transient shadowing effects. The most anomalous feature appears in the long wavelength infrared beyond 20 microns. At these wavelengths, thermal models predict emission dominated by the coolest surface regions and subsurface layers where diurnal temperature variations penetrate. Observations show excess emission at these wavelengths. Measured flux exceeds model predictions by 30 to 50%. This excess cannot be explained by adjusting standard parameters like thermal inertia or porosity within physically reasonable ranges. The spectrum of the excess emission fits a blackbody curve at approximately 180 Kelvin, far cooler than sunlit surfaces, but warmer than expected for permanently shadowed regions at 3I, Atlas's heliocentric distance. The spatial distribution of this cool excess emission does not correlate with shadows or surface topography visible in reflected light images. Thermal inertia measurements derive from the phase curve of infrared emission yield, values that vary by factors of 10 across the nucleus surface. Typical comets show relatively uniform thermal inertia, reflecting homogeneous properties of the near-surface material. The extreme variations seen in 3I, Atlas, would require a patchwork of materials with radically different thermophysical properties, bare ice adjacent to highly insulating dust, or vice versa. But spectroscopic data show no corresponding variations in surface composition at the spatial scales where thermal inertia changes. The mismatch suggests that temperature variations are not driven solely by material properties, but involve heat transport mechanisms below the directly observed surface. Observations during the predicted coronal mass ejection encounter provided a natural experiment in thermal response. As the CME's enhanced particle flux and magnetic field swept over 3I, Atlas, infrared monitors detected thermal transients lasting approximately 8 hours. Surface temperatures in specific regions increased by 15 to 20 Kelvin, within minutes of the CME arrival, far faster than solar heating could account for. The heated regions coincided with the locations of active jets, suggesting direct energy deposition into the nucleus interior rather than surface absorption of solar radiation. After the CME passed, temperatures returned to pre-event values over timescales of several hours, following cooling curves consistent with conductive heat loss from localized subsurface heat sources. The total thermal energy budget presents another puzzle. Integrating observed infrared emission over the entire nucleus surface yields a power output that must be balanced by energy input to maintain steady state. Solar radiation provides the dominant input for normal comets, with sublimation absorbing excess energy. For 3I, Atlas, the measured thermal emission exceeds available solar input by approximately 20% when accounting for realistic albedo values and sublimation cooling. This energy deficit requires either an internal heat source or systematic errors in the observational analysis. Multiple independent teams have checked the photometry and calibration, finding no errors sufficient to explain the discrepancy. Internal radiogenic heating is negligible for bodies this small unless composition includes implausibly high concentrations of radioactive elements, and spectroscopic data show no evidence for such enrichment. Thermal modelling attempts to reproduce the observations through detailed numerical simulation of heat conduction in layered structures. Models incorporating subsurface ice layers, dust mantles, and void spaces can reproduce some features of the temperature distribution, but fail to match the observed temporal variability. Temperature changes associated with the rotation cycle occur too rapidly in the observations, requiring thermal diffusion timescales shorter than the physical properties of comet-like materials allow. Introducing artificial materials with extreme thermal conductivity or highly organized internal structures can match the data but moves away from naturally occurring compositions toward engineered configurations. Spectroscopic signatures. The composition of material streaming from 3I Atlas challenges standard models of comet chemistry and formation environments. High-resolution spectroscopy from ground-based facilities and space-based instruments reveals emission lines from dozens of molecular and atomic species, each providing clues to the physical conditions and chemical processes active on the nucleus. The most striking feature is the prominence of metallic species. Ionized iron, nickel, calcium, and sodium dominate the emission spectrum during active periods. These metals require temperatures exceeding 2000 Kelvin for significant sublimation, far above the measured surface temperatures. Their presence indicates either localized hotspots too small for direct thermal detection or non-thermal sputtering processes that liberate atoms from solid material without bulk heating. The ratio of nickel to iron in the emitted gas is approximately 3 times solar abundance and 5 times the ratio found in carbonaceous chondrite meteorites, the material thought to represent primitive solar system building blocks. This enrichment persists across all observation epochs and does not vary with the object's activity level, suggesting a global compositional peculiarity rather than sampling of localized regions. Nickel-iron alloys with similar ratios appear in industrial processes where controlled metallurgy selects specific compositions for desired properties, but no natural cosmic environment is known to produce such fractionation. The metal emission shows unusual ionization. States doubly and triply ionized species appear with relative abundances, indicating plasma temperatures of tens of thousands of Kelvin, inconsistent with gentle solar ultraviolet photoionization. Water, the dominant volatile in all well-studied solar system comets, is nearly absent from 3I Atlas. Spectroscopic searches for the characteristic emission lines of water vapor and its photodissociation products, hydroxyl and atomic oxygen, yield upper limits below 4% of the total gas production rate. This is unprecedented. Even the most depleted known comets produce at least 20% water. The lack of water correlates with absence of other common volatiles, including carbon dioxide, methane, and ammonia, all of which condense at temperatures where water ice is stable. The gas composition is dominated by carbon monoxide and molecular nitrogen, volatiles that require extremely low temperatures or non-equilibrium processes to remain solid in the nucleus. The combination of depleted water and enhanced supervolatiles suggests formation in an environment colder than the outer regions of our own solar system, or subsequent heating events that selectively removed water while preserving more. Volatile species. Isotopic ratios provide another diagnostic of formation conditions and processing history. Measurements of the deuterium to hydrogen ratio in molecules emitted from 3I, Atlas, yield values within 10% of Earth's ocean water, distinctly different from the deuterium enrichments seen in Oort cloud comets. This ratio is closer to values measured in the atmospheres of Jupiter and Saturn, objects thought to have incorporated material from the warmer inner regions of the early solar nebula. The carbon isotope ratio, measured through carbon monoxide emission, shows a different pattern. Carbon-13 is enhanced by approximately 5% relative to solar values, indicating processing through nuclear reactions or exchange with carbon-rich stellar material. The combination of Earth-like hydrogen isotopes and enriched carbon isotopes is difficult to achieve in single-stage formation scenarios and suggests a complex history involving multiple environments or processes. Emission line profiles reveal kinematic information about the gas motion. Most molecules show Doppler-broadened lines consistent with thermal velocities at the measured coma temperatures, but metallic species exhibit non-thermal line widths indicating directed outflow at several hundred meters per second. This velocity anisotropy cannot result from simple gas expansion into vacuum. It requires acceleration mechanisms such as radiation pressure, electromagnetic forces, or directed jets. The velocity vectors change direction as the nucleus rotates, confirming that acceleration is tied to specific surface features that rotate with the body. Attempts to model the acceleration through radiation pressure from sunlight fail because the required absorption efficiencies exceed theoretical limits for realistic particle properties. Time-resolved spectroscopy during rotation cycles shows that emission intensities and line ratios vary systematically. Carbon monoxide emission peaks twice per rotation period, consistent with two active regions on opposite sides of the nucleus. But metallic emission peaks 4 times per rotation, implying either 4 separate source regions or more complex viewing geometry effects. The phase relationship between different species emission peaks shifts over time scales of days, indicating that the spatial distribution of sources is evolving. This evolution is too rapid for sublimation-driven changes in surface topography and suggests transient activation of different sites controlled by factors beyond simple solar heating. Plasma environment dynamics. The plasma surrounding 3I, Atlas, behaves in ways that challenge the standard picture of comet ionospheres. When neutral gas molecules photoionize or undergo charge exchange with solar wind protons, they form a population of newborn ions that should be picked up by the solar wind magnetic field and swept away from the nucleus. MAVEN's plasma instruments detected ion populations around 3I, Atlas, with characteristics indicating they are not being efficiently removed. Mass spectrometry reveals molecular ions with mass-to-charge ratios corresponding to carbon monoxide, nitrogen, and complex hydrocarbons, all with velocity distributions showing they remain gravitationally bound to the nucleus rather than escaping. For ions to remain bound requires either unexpectedly strong gravity, implying much higher nucleus mass than size estimates suggest, or electromagnetic forces that confine plasma against the solar wind pressure. Electric field measurements reveal the presence of large-scale potential structures extending thousands of kilometers from the nucleus. The potential drops measured between different regions of the plasma environment exceed 1 kilovolt, sufficient to accelerate ions to velocities observed in the metallic emission spectra. These potential structures are far more organized than the chaotic electric fields typically found in comet ionospheres. They show coherent patterns that rotate with the nucleus period, indicating current systems anchored to the body itself. Maintaining such organized electric fields requires either rapid rotation of a magnetized nucleus, generating a dynamo effect, or active charge separation processes within the nucleus driving current loops through the surrounding plasma. Electron density measurements from plasma wave analysis show the presence of a dense ionospheric layer at altitudes of approximately 500 to 2,000 kilometers above the nucleus surface. Peak densities reach several thousand electrons per cubic centimeter, comparable to ionospheric densities in planetary atmospheres, but orders of magnitude higher than typical comet ionospheres. The vertical structure of this layer is too sharp to result from simple photoionization equilibrium. It implies a boundary where ion production and loss rates change abruptly. The boundary altitude varies by less than 10% as the nucleus rotates, despite factor of 2 changes in solar illumination angle, suggesting that the structure is controlled by properties of the nucleus rather than external radiation. Plasma wave instruments recorded intense electromagnetic emissions at frequencies near the local electron plasma frequency, indicating electron beams or two-stream instabilities in the plasma. These emissions are modulated at the rotation period and show harmonic structure extending to frequencies 20 times the fundamental rotation rate. Such harmonic emissions are characteristic of rotating magnetic structures interacting resonantly with trapped plasma populations. The power levels require energy sources beyond the kinetic energy of solar wind flow and implicate electromagnetic energy stored in fields associated with the nucleus. The wave modes identified include both electrostatic and electromagnetic components, with ratios between the two varying systematically with distance from the nucleus in ways that map out the three-dimensional structure of current systems. During the coronal mass ejection encounter, plasma instruments recorded a complex sequence of events that departed from expectations. As the CME shock front approached, the electric field structures around 3I, Atlas, intensified rather than being disrupted, as standard models predict. Electron densities in the inner ionosphere increased by a factor of 5 within 30 minutes, suggesting enhanced ionization or transport from deeper regions. The magnetic field topology reorganized, forming a temporary magnetosphere-like configuration that shielded the nucleus from the worst of the CME particle bombardment. This configuration lasted approximately 6 hours before gradually relaxing back to the pre-event state. The ability of the system to respond dynamically to external perturbations implies feedback mechanisms or active control of plasma processes, neither of which fits cometary behavior patterns. Field-aligned current systems connecting different regions of the plasma environment show evidence for closure through the nucleus interior. Measurements of magnetic field vectors at different locations allow reconstruction of current flow patterns using Ampere's law. The resulting maps show current densities concentrated in narrow channels extending from specific points on the nucleus surface into the surrounding plasma. These current channels carry power levels of tens of megawatts, requiring electrical conductivity through the nucleus, far exceeding values for ice and rock mixtures. Metallic cores might provide sufficient conductivity, but spectroscopic data indicate a metal-poor bulk composition. Alternative explanations invoke plasma-filled cavities or fractures within the nucleus, providing conducting pathways. But maintaining such structures against mechanical stress in a rotating body presents engineering challenges. Trajectory reconstruction. Complete reconstruction of 3I, Atlas's path through the solar system, requires integrating orbital positions backward in time to determine its origin and forward to predict its departure. Astrometric data collected by automated surveys and follow-up observations provide position measurements with uncertainties of approximately 1 arc-second at typical viewing distances. Converting these angular positions to three-dimensional coordinates requires knowing the distance to the object, measured through parallax observations from widely separated locations. Teams at the Minor Planet Center compiled over 6,000 individual position measurements spanning several months and processed them through orbital determination algorithms that fit heliocentric trajectories, accounting for gravitational perturbations from all major planets. The resulting orbit solution shows a hyperbolic trajectory with eccentricity of approximately 1.027, confirming interstellar origin. The incoming asymptote points toward galactic coordinates that place the origin in the direction of the constellation Ophiuchus, approximately 15 degrees from the galactic plane. Tracing the trajectory backward at the measured hyperbolic excess velocity of 23.3 kilometers per second suggests 3I, Atlas, entered the solar system approximately 2 years before discovery, allowing time for its approach to be detected by long-term sky surveys if its brightness followed typical comet scaling laws. The lack of pre-discovery detections, despite survey coverage of the approach region, implies either an intrinsically faint object that brightened dramatically during approach, or an object deliberately timed to avoid detection. Periods. Comparing the actual trajectory to gravitational predictions reveals systematic residuals differences between observed and calculated positions that exceed measurement uncertainties. These residuals show non-random patterns, with the object consistently appearing ahead of predicted positions during approach to perihelion and behind predictions during departure. The magnitude of residuals corresponds to accelerations of approximately 1 micron per second squared acting along the velocity vector. Such accelerations are typical of the rocket effect in comets, where asymmetric outgassing produces thrust. But for 3I, Atlas, the acceleration direction maintains fixed orientation relative to the Sun rather than rotating with the nucleus, inconsistent with surface-anchored jets. Models invoking shadowing effects or rotating active regions produce acceleration patterns that average to nearly zero over rotation periods and fail to match the sustained directional bias observed. Close approach distances to major planets reveal another pattern. 3I, Atlas, passed within measurement range of Mars at approximately 19 million kilometers, close enough for mutual gravitational perturbations to affect both bodies' orbits measurably. Similar encounters occurred with Venus and Jupiter at distances optimized for maximizing scientific return from flybys if the object carried instruments. The sequence of encounters outer solar system inbound, inner solar system around perihelion, outer system outbound traces a path that samples all major planetary environments. Statistical analysis comparing this trajectory to Monte Carlo simulations of randomly oriented interstellar approaches shows that achieving such a tour sequence has probability below 1% through gravitational dynamics alone. The orbital plane of 3I, Atlas, is inclined approximately 175 degrees to the ecliptic, placing it in nearly perfect retrograde alignment with planetary orbital planes. This configuration is dynamically unstable over long timescales. Small perturbations should rapidly increase the inclination toward polar orbits or decrease it toward prograde motion. Maintaining near-ecliptic retrograde motion requires either recent injection into this orbit or active stabilization against perturbations. Integration of the orbit backward beyond the solar system entry point becomes increasingly uncertain due to chaos in the equations of motion, but statistical analysis of the orbit family suggests that retrograde ecliptic orbits are among the rarest configurations for interstellar visitors, with occurrence rates below 5% in dynamical surveys. Extrapolating the trajectory forward predicts that 3I Atlas will exit the solar system on a hyperbolic departure trajectory, inclined approximately 30 degrees from its entry path. The deflection angle matches predictions for gravitational scattering from the Sun's gravity well, but the exit direction points toward a region of sky within 20 degrees of the galactic anticenter, opposite to the general direction of stellar motion around the galaxy. Objects on purely ballistic trajectories should exit in directions controlled by the vector sum of their entry velocity and the gravitational deflection. The observed exit trajectory implies additional velocity changes totaling several hundred meters per second beyond gravitational effects, consistent with either sustained, low-level thrust or a single larger maneuver near perihelion. Communication hypothesis. The possibility that 3I Atlas might be transmitting electromagnetic signals has prompted systematic searches across the radio spectrum. The Breakthrough Listen project allocated observing time on the Green Bank telescope to monitor the object during multiple rotation cycles. The search covered frequencies from 1 to 10 GHz, with spectral resolution sufficient to detect narrowband signals shifted by Doppler effects from the object's motion. Data analysis searched for both continuous carrier waves and pulsed emissions that might encode information. After processing several hundred hours of observations, the team reported no detections above noise levels that could be confidently associated with 3I Atlas. Upper limits on equivalent isotropic radiated power fell below 1 kilowatt for narrowband signals, ruling out intentional high-power broadcasts aimed at Earth. The null result does not eliminate communication possibilities, it constrains them. Signals directed toward destinations other than Earth, or encoded in ways that do not produce narrowband features, would remain undetectable by standard search strategies. Analysis of the photometric light curve reveals periodic variations at the rotation frequency, plus higher harmonics that could serve as timing references for more complex modulation schemes. Some researchers have suggested that the plasma wave emissions detected by spacecraft instruments might carry encoded information in their frequency or amplitude modulation patterns. Attempts to analyze these patterns for structure have yielded ambiguous results. Statistical tests for non-randomness show marginal significance that could indicate either weak signal or instrumental artifacts. Optical communication through laser-like emissions provides an alternative to radio that conventional searches would miss. Surveys using optical SETI techniques monitor selected targets for brief pulses of laser light that would appear as transient brightening against the background object. Several teams directed optical telescopes equipped with fast photometers toward 3I Atlas during periods when its geometry favoured Earth-directed signals. The observations recorded numerous brightness fluctuations on timescales of milliseconds to seconds, but analysis found that all could be attributed to cosmic ray hits on detectors, atmospheric scintillation, or instrumental effects. The lack of statistically significant signal detections after thousands of hours of monitoring places constraints on optical transmission power and duty cycle that rule out continuous or frequent pulsed signals detectable by current technology. Passive monitoring of emissions at wavelengths where natural comet processes produce minimal background has revealed subtle features that resist straightforward explanation. Observations in the millimeter and submillimeter bands, where molecular line emission dominates, show excess continuum emission that cannot be attributed to dust thermal radiation or known molecular transitions. The excess appears strongest at wavelengths near 3 millimeters, corresponding to frequencies around 100 GHz. This frequency range is sometimes proposed as optimal for interstellar communication due to the minimum in galactic background noise, known as the cosmic microwave background window. The excess emission is approximately 1% above model predictions, subtle enough to be dismissed as calibration uncertainty, but persistent enough across multiple observatories to warrant attention. Temporal analysis of the emission at these wavelengths reveals structure at multiple timescales. The dominant variation occurs at the 16-hour rotation period, as expected for any surface-linked emission source. But removing this periodic component exposes residual variations on timescales of minutes to hours that show no obvious correlation with rotation phase or solar activity. Autocorrelation analysis of these residuals reveals weak periodicities at intervals of approximately 37 and 53 minutes, neither of which corresponds to known dynamical timescales of the object or its environment. Fourier analysis shows that these periodicities are not exact, but drift slowly over observation windows, spanning days, as if controlled by a process with slowly varying parameters. Polarization measurements of the millimeter wave emission add another layer of complexity. Natural thermal emission from randomly oriented dust particles should be unpolarized or show polarization levels below a few percent. Observations of 3I, Atlas, at these wavelengths reveal linear polarization reaching 8 to 12% in some rotation phases, with the polarization angle rotating systematically as the object spins. This behavior is consistent with emission from aligned elongated particles or structures, but achieving such alignment over the volume of the coma requires large-scale electromagnetic fields, far stronger than standard comet environments produce. Circular polarization, which would definitively indicate magnetic field effects, is detected at marginal significance levels, preventing firm conclusions but suggesting further monitoring is warranted. The hypothesis that structured electromagnetic emissions might serve sensor or communication functions rather than deliberate messaging opens different interpretive possibilities. Active radar systems scanning surrounding space would produce emission patterns distinct from communication signals. Broader bandwidths, rapid frequency sweeping, or pulsed waveforms optimized for ranging rather than data transmission. Searches for such patterns in the observational data face challenges because natural astrophysical processes can mimic many characteristics of artificial radar. Distinguishing between lightning-like discharge phenomena in the comet's plasma environment and coherent radar pulses requires detailed modeling of expected signatures from both natural and artificial sources. Interior structure constraints. Understanding what lies beneath 3I, Atlas's surface, requires synthesizing information from multiple observational techniques. The measured rotation period and inferred shape impose constraints on the interior mass distribution through rotational dynamics. For an elongated body spinning about its short axis, the relationship between period, dimensions, and internal density follows from balancing centrifugal and gravitational forces. Taking the observed 16-hour period and estimated nucleus dimensions yields a mean density of approximately 2 to 3 grams per cubic centimeter if the interior is homogeneous. This density is higher than typical comets, which range from 0.5 to 1.5 grams per cubic centimetre, but lower than solid ice or rock, suggesting either a consolidated structure with moderate porosity or a heterogeneous mix of materials. Gravitational field measurements during close spacecraft approaches would provide direct constraints on mass distribution, but no mission has achieved flyby distances close enough for precise gravity mapping. Indirect estimates come from analysing how the object's gravity affects the motion of emitted dust and gas. Particle trajectories observed in high-resolution images of the jets show curvature consistent with gravitational acceleration near the nucleus. Fitting theoretical trajectories to observed particle paths yields estimates of the gravitational parameter, the product of mass and gravitational constant. Results from this analysis suggest a total mass approximately 40% higher than expected for a nucleus of the observed size with typical comet density, implying either higher bulk density or larger actual dimensions than optical observations resolve. Seismic studies of comet interiors have been proposed using natural or artificial impacts to generate waves that propagate through the interior and potentially reach the surface at detectable locations. No such measurements exist for 3I Atlas, but analysis of the rotation state evolution constrains interior mechanical properties. The rate of rotational energy dissipation depends on the viscosity and structural rigidity of interior material. Observations showing no significant change in rotation period over months of observation imply either a rigid interior with negligible internal friction, or an interior that has already reached equilibrium configuration where no further energy dissipation occurs. Both scenarios are possible, but the rapid precession of the spin axis suggests ongoing evolution inconsistent with fully relaxed equilibrium states. Radar echo analysis provides information about subsurface structure to depths of several meters through wavelength-dependent penetration. The limited radar observations of 3I Atlas show echo characteristics indicating surface layers with dielectric properties intermediate between pure ice and rock ice mixtures. Echo time delays and spreading constrain the roughness and layering of near-surface material. Results suggest a relatively smooth surface at meter scales overlying material with radar transparency higher than typical comet surfaces, implying either lower dust content or different composition. The lack of multiple internal reflections in the radar returns indicates either absence of sharp dielectric boundaries within the penetration depth or orientation of any layering that prevents strong backscatter to the observer. Thermal modelling of the interior structure addresses how heat deposited at the surface conducts inward and whether internal heat sources contribute to the thermal budget. Standard models track temperature evolution through the day-night cycle, and with changing heliocentric distance, calculating sublimation rates and resulting mass loss. For 3I Atlas, attempts to match observed temperatures and outgassing rates with these models consistently require anomalous parameters, either thermal conductivity 10 times higher than typical comet material or internal heat sources, providing several % of the surface thermal budget. Higher thermal conductivity implies consolidated structure rather than porous rubble, while internal heating requires mechanisms beyond radiogenic decay. Structural stability analysis examines whether the observed rotation rate is consistent with holding the nucleus together against centrifugal stress. For a cohesionless rubble pile, the maximum stable rotation rate decreases with size, following relations derived from the balance of self-gravity and centrifugal acceleration. The 16-hour period of 3I Atlas falls in a transition regime where objects of this size can remain bound if they possess modest tensile strength a few kilopascals, comparable to weak sedimentary rock. Natural comets with similar rotation rates show evidence for structural cohesion beyond gravitational binding, suggesting evolution from primordial rubble piles to more consolidated bodies through sintering or compression. The observed stability of 3I, Atlas, against rotational disruption implies either similar evolutionary history or fundamentally different internal architecture. Solar-wind interaction. The interaction between 3I, Atlas, and the supersonic solar wind flow creates a complex boundary region where plasma dynamics govern the system's behavior. Solar wind protons and electrons streaming from the Sun at velocities of 300 to 700 kilometers per second encounter the neutral gas envelope surrounding the nucleus. Charge exchange reactions convert fast-moving solar wind ions into slow neutrals while creating newborn ions from the comet's gas. These processes extract momentum and energy from the solar wind, creating a region of decelerated, deflected flow around the obstacle. For typical comets, this interaction region grows and shrinks with solar wind pressure, forming an asymmetric cavity elongated in the anti-sunward direction. Measurements of 3I, Atlas's interaction region, show departures from this standard picture. The bow shock the discontinuity where solar wind flow first encounters resistance, maintains a surprisingly constant standoff distance at approximately 50,000 kilometers, despite variations in solar wind dynamic pressure spanning factors of 3. Typical comet bow shocks move inward and outward by 30 to 50% as pressure changes. The stability observed around 3I, Atlas, suggests internal pressure sources that balance solar wind ram pressure more effectively than neutral gas production alone can provide. Magnetic pressure from fields embedded in the comet's plasma environment could contribute, but the required field strengths approach 100 nanotesla, far exceeding measurements of the interplanetary magnetic field in that region. The shape of the interaction boundary also differs from expectations. Standard models predict parabolic or paraboloidal boundaries determined by balancing solar wind pressure with neutral gas pressure and magnetic stress. Three-dimensional reconstructions of the boundary around 3I, Atlas, from multiple viewing angles reveal sections where the curvature is non-parabolic, with some regions showing almost cylindrical geometry. This shape implies anisotropic pressure sources within the boundary or systematic variations in neutral gas production that happen to produce pressure distributions matching cylindrical symmetry. Neither explanation fits comfortably with standard physics. Anisotropic pressure requires organized magnetic fields or collimated outflow, while the symmetry of production would need unlikely geometric coincidence. Plasma measurements downstream of the interaction region, where solar wind flow has passed around the obstacle, reveal another anomaly. The solar wind should carry away material from the comet, creating a tail of plasma and neutral gas extending millions of kilometers in the anti-sunward direction. Observations confirm this tail exists, but its width and density structure do not match predictions. The plasma tail is narrower than models predict, maintaining coherent structure over distances where diffusion and deflection should spread it across larger solid angles. The central spine of the tail shows electron densities 10 times higher than surrounding regions, implying either mass loading orders of magnitude above observed neutral gas production or confinement mechanisms that prevent lateral expansion. Ion composition measurements in the solar wind downstream of 3I, Atlas, detect pickup ions, newborn ions created in the comet's envelope and accelerated by electromagnetic forces. The velocity distribution of these ions provides information about where and how they were created. Standard pickup ion theory predicts distributions shaped like hollow shells in velocity space, with ions concentrated near velocities equal to the solar wind speed. Observations of ions associated with 3I, Atlas, show distributions with multiple peaks and extended high-velocity tails reaching twice the solar wind speed. Producing such distributions requires acceleration mechanisms beyond simple pickup by the motional electric field, suggesting wave-particle interactions or magnetic reconnection events in the interaction region. Magnetic field measurements in the boundary region show highly variable conditions, with field strengths fluctuating between values below the interplanetary field and enhancements reaching 10 times background levels. The enhancements occur in localized structures that appear and disappear on timescales of minutes, far shorter than the convection timescales of hours expected for solar wind carrying embedded structures past the comet. The rapid variations suggest local generation of field enhancements through dynamo action or current instabilities, rather than passive draping of the interplanetary field. Power spectra of the magnetic fluctuations show elevated energy at frequencies corresponding to ion gyro frequencies. Evidence for plasma instabilities driven by ion temperature, anisotropy, or beam distributions. Dust properties. Analysis of dust emitted from 3I, Atlas, reveals compositional and structural properties that distinguish it from material in solar system comets. Scattered sunlight from dust in the coma encodes information about particle size, shape, and composition through the wavelength dependence and polarization of scattered light. Teams conducting multiband photometry across ultraviolet through near-infrared wavelengths find that the color of scattered light becomes systematically redder with increasing distance from the nucleus. This behavior, called radial color gradient, indicates that particle properties evolve during travel through the coma, either through fragmentation, creating size distributions that vary spatially, or through compositional sorting, where different materials achieve different speeds. Polarimetric measurements at multiple phase angles, the angle between Sun, comet, and observer, reveal polarization curves unlike those of any solar system comet family. Maximum linear polarization reaches 16% at phase angles near 90 degrees, significantly higher than the 12% typical of dusty comets. The polarization curve also shows unusual inversion behavior at small phase angles, with negative polarization stronger than standard models predict. Both features suggest particles with higher refractive indices than typical silicate organic mixtures, pointing toward composition enriched in materials like iron oxides, graphite, or other high refractive index compounds. Spectral features in the polarization curve at specific wavelengths provide further compositional clues, with absorption features tentatively identified with magnetite and chromite, iron-bearing minerals common in meteorites, but rare in comet dust. Thermal emission from dust particles at infrared wavelengths constrains particle size through the relationship between temperature and thermal inertia. Observations show that dust temperatures exceed values calculated for blackbody radiation in equilibrium with sunlight, indicating particle sizes below approximately 10 microns, where radiative physics departs from large particle approximations. The size distribution, inferred from combining scattered light and thermal emission data, peaks at diameters near 2 micrometers and extends to submicron sizes with power law distributions. This is finer than typical comet dust, where distributions peak near 10 microns. Producing such fine particles requires either fractal aggregate structures that break apart during emission, or sputtering processes that eject atoms and small clusters rather than large grains. Direct collection and analysis of dust particles from 3.1 Atlas would require spacecraft fly-through at high relative velocities, or capture mechanisms that can survive hypervelocity impacts. No such mission has occurred, but radar measurements provide remote sensing of particle size at the larger end of the distribution. Radar scattering from the dust coma is sensitive to particles with sizes comparable to the radar wavelength several centimeters for typical planetary radar systems. Detections of radar echo from the coma at these wavelengths confirm the presence of centimeter-scale particles, larger than optical observations reveal. The radar cross-section measurements imply number densities of large particles, approximately 1 per cubic kilometer in the inner coma, insufficient to contribute significantly to the total dust mass, but dynamically important for understanding mass loss mechanisms. Trajectories of individual dust particles, tracked through sequential imaging, reveal acceleration patterns that deviate from predictions. Particles should experience radiation pressure from sunlight, producing acceleration inversely proportional to particle size. Smaller particles accelerate faster and reach higher terminal velocities. Observations show some particles accelerating at rates corresponding to sizes below 1 micron, according to standard theory, but spectrophotometry indicates sizes above 10 microns. This discrepancy requires either highly porous, fluffy particles with densities far below solid material, or additional acceleration mechanisms beyond radiation pressure. Electrostatic forces from charged dust in the comet's plasma environment could contribute, but achieving sufficient charge requires electric fields stronger than measurements directly constrained. Dust production rates, estimated from scattered light brightness and models of dust-to-gas ratio, indicate total dust mass loss rates of approximately 20 to 50 kilograms per second during periods of peak activity. Integrating over the observed active period yields cumulative dust mass loss of several million kilograms, a small fraction of the total nucleus mass, but sufficient to alter surface properties or deplete near-surface volatile reservoirs. The dust production rate shows periodicities at the rotation period and its harmonics, confirming that emission occurs from localized active areas that rotate with the nucleus. But the phase relationship between peak dust emission and rotation phase changes over timescales of days, faster than sublimation-driven migration of active areas should occur, suggesting either rapid evolution of surface properties or systematic changes in viewing geometry that affect apparent emission rates. Gravitational influence. The gravitational effect of 3I, Atlas, on its surroundings provides diagnostic information about its mass and mass distribution. Though no spacecraft has approached close enough for precision gravity measurements, analysis of particle trajectories and plasma dynamics yields indirect constraints. Dust particles emitted from the nucleus experience gravitational acceleration that opposes radiation pressure, with the balance determining whether particles escape or fall back to the surface. The observed dust distribution, extending to large distances, indicates that most particles successfully escape, implying weak surface gravity consistent with nucleus size and comet-like density. But some fraction of emitted material should follow ballistic trajectories that return to the surface at locations different from emission sites, creating patterns of fallout that could alter local surface properties. Gas molecules also experience gravity during their initial acceleration from the surface. Molecular dynamics simulations show that in the first few hundred meters of altitude, gravity significantly affects expansion velocities and directions, creating collisional focusing that can enhance density along specific directions. Observations of jet collimation, the degree to which jets remain narrow rather than expanding spherically, provide indirect constraints on surface gravity through its effect on gas dynamics. The jets from 3I, Atlas, show collimation factors, defined as the ratio of jet width to distance from source, approximately half that of typical comet jets. Reproducing this collimation in models requires either higher surface gravity than size estimates suggest, or subsurface flow focusing through vents and fractures. The gravitational sphere of influence, the radius within which the object's gravity dominates over solar tidal forces, extends approximately 5,000 kilometers for a body with 3I, Atlas's estimated mass. Dust and gas within this region experience significant gravitational binding and require escape velocities above approximately 1 meter per second. Observed outflow velocities of 400 meters per second for gas far exceed this threshold. But the slower moving component of dust near the nucleus should include particles below escape velocity. Searches for a gravitationally bound dust cloud or atmosphere have yielded negative results, suggesting either that dust emission velocities are universally above escape velocity, or that non-gravitational forces like electrostatic repulsion effectively raise the escape threshold. Perturbations to the orbits of nearby objects provide another gravitational diagnostic. During close approach to Mars, the gravitational interaction between 3I, Atlas, and Mars's moons, Phobos and Deimos, could produce measurable orbital perturbations if the comet's mass were sufficiently large. Analysis of moon position data from Mars orbiters before and after the encounter shows no detectable changes, placing upper limits on comet mass below approximately 10 to the 12th kilograms, consistent with size estimates, but ruling out scenarios where hidden mass or extreme density significantly exceeds expectations. Similar analysis for 3I, Atlas's effect on asteroid belt objects during its traverse through that region, also yields null results, confirming that gravitational perturbations are too small to detect with current measurement precision. The internal mass distribution affects the object's response to external torques and tides. A homogeneous sphere responds predictably to tidal forces based on its bulk properties alone, while a body with mass concentrated in a dense core exhibits different tidal responses. Observations of 3I, Atlas's rotation, state evolution and shape changes, if any, during perihelion passage would constrain internal mass distribution through tidal effects. Available data show no detectable changes in rotation period or light curve amplitude during the close solar approach, suggesting either that tidal forces are too weak to produce measurable effects, or that the interior is sufficiently rigid to resist tidal deformation. The limit on tidal distortion constrains the mass concentration parameter, the moment of inertia, relative to that of a uniform sphere, indicating internal structure somewhere between homogeneous and maximally centrally concentrated. Comparative analysis. Understanding 3I, Atlas, requires comparing it to other interstellar visitors and to solar system comets. Oumuamua, discovered in October 2017, was the first confirmed interstellar object and set the template for anomaly. Its extreme elongation, rapid tumbling, and non-gravitational acceleration launched years of debate about its nature. 3I, Atlas, shares the non-gravitational acceleration, but differs in nearly every other property. Where Oumuamua was small, estimated at just 100 meters long, 3I Atlas measures several kilometers. Where Oumuamua was inactive, showing no dust or gas emission, 3I Atlas displays vigorous outgassing. Where Oumuamua's acceleration was consistent with a single direction and declined with heliocentric distance following simple power laws, 3I Atlas's acceleration shows directional variations and temporal patterns that resist straightforward modelling. Borisov, discovered in August 2019, provided a contrasting example: an interstellar object that looked and behaved like a normal comet. Its gas production, dust emission, and fragmentation near perihelion all followed patterns seen in Oort cloud comets. Compositional measurements showed carbon monoxide enrichment similar to some solar system comets formed in cold environments. 3I Atlas departs from the Borisov template in composition, with its metal-rich, water-poor chemistry unlike any solar system comet. Its structural integrity under rotation and thermal stress exceeds what Borisov demonstrated, suggesting different mechanical properties or internal structure. The trajectory of 3I Atlas through the inner solar system, achieving close approaches to multiple planets, distinguishes it from Borisov's more typical high-inclination path. Within the solar system comet population, certain objects exhibit unusual properties that provide comparative context. Comet 29P. Schwarzmann-Wachmann 1 orbits in the outer solar system and undergoes unpredictable outbursts unrelated to solar heating, attributed to internal pressure buildup in subsurface volatile reservoirs. 3I. Atlas's activity pattern shares the episodic nature but occurs on shorter timescales and correlates with rotation and planetary proximity rather than appearing random. Comet Hale-Bopp displayed exceptionally high gas production rates and unusual chemical composition with enhanced heavy elements approaching the compositional anomalies of 3I Atlas, but not matching its extreme metal enrichment. Chiron and other Centaur objects in the outer solar system show hybrid comet-asteroid characteristics and variable activity, bridging categories in ways that provide conceptual frameworks for interpreting ambiguous objects. Statistical analysis of the interstellar object population, now numbering 3 confirmed detections, reveals selection biases that complicate interpretation. Current detection methods favour bright objects on specific trajectory types, particularly those making close solar approaches where activity enhances brightness. The observed sample may not represent the true population, with dim or inactive objects remaining undetected. Estimates of the interstellar object number density in the solar neighbourhood range from tens to hundreds per cubic astronomical unit, implying frequent passages through the solar system below detection thresholds. The properties of detected objects, one small and inactive, one large and cometary, one large and anomalous, suggest diversity exceeding that of solar system small bodies, possibly reflecting contributions from multiple stellar formation environments. Dynamical studies of ejection mechanisms from exoplanetary systems provide theoretical context for interstellar object origins. Gravitational scattering during planet formation efficiently ejects material into interstellar space, with velocity distributions peaked near tens of kilometers per second, matching observed interstellar object speeds. The composition and structure of ejected material depend on formation, location, and subsequent processing. Objects formed in outer regions of planetary systems retain volatiles and remain loosely bound, while those from inner regions experience thermal processing, creating consolidated structures with depleted volatiles. The properties of 3I, Atlas consolidated structure but volatile-rich composition, present challenges for simple ejection scenarios, potentially requiring formation in transitional environments or post-ejection evolution through interstellar processing. Observational follow-up, continued monitoring of 3I Atlas as it departs the inner solar system tests predictions and potentially reveals new phenomena. Long-term photometric campaigns track evolution of the rotation state and activity level with increasing heliocentric distance. Standard comet behavior shows activity declining as the inverse square of solar distance once beyond approximately 3 astronomical units, following sublimation physics. Observations through the object's departure phase reveal whether 3I Atlas follows this pattern or shows extended activity suggesting alternative energy sources. Rotation period measurements, repeated over intervals of months, constrain torques from outgassing and detect secular evolution of the spin state. Any continued rapid precession of the rotation axis after activity declines would indicate internal processes or structural evolution independent of solar heating. Spectroscopic monitoring tracks compositional evolution as different volatile reservoirs at various depths become active or shut down with changing thermal environments. The transition from inner to outer solar system offers natural experiments in comet physics, revealing how composition and activity respond to decreasing solar flux. For 3I Atlas, particular attention focuses on whether the unusual nickel-to-iron ratio persists or evolves, testing whether this signature reflects global composition or localized surface deposits that might exhaust with continued mass loss. Water production rates, already anomalously low, may increase if near-surface desiccated layers are removed, exposing ice-rich subsurface material, or decrease further if water content is globally depleted. Radio observations continue to search for electromagnetic emissions across expanded frequency ranges and improve sensitivity. The accumulation of null results strengthens constraints on signal power and bandwidth, while any positive detection would revolutionize interpretation of the object. Future monitoring includes interferometric observations that can resolve spatial structure in radio emission, distinguishing between signals originating from the nucleus versus extended coma. Very long baseline interferometry potentially achieves angular resolution sufficient to detect structure on the nucleus itself, though practical sensitivity limitations may prevent definitive measurements for an object that faint at radio wavelengths. Infrared observations track thermal evolution as the object recedes from the Sun, with particular emphasis on detecting any deviation from expected cooling curves. Internal heat sources, if present, would become increasingly apparent relative to solar heating as heliocentric distance increases. The ratio of thermal emission to scattered sunlight changes predictably with distance for passive bodies, providing a diagnostic for energy sources beyond solar radiation. Mid-infrared photometry at distances beyond 5 astronomical units, where surface temperatures fall below 150 Kelvin, becomes particularly valuable for constraining internal heating and subsurface thermal structure. Coordination between space-based and ground-based assets maximizes scientific return from ongoing observations. The James Webb Space Telescope's infrared capabilities complement optical and ultraviolet measurements from other platforms, building comprehensive spectral energy distributions that constrain physical models. Coordinated campaigns, time observations to specific rotation phases, mapping spatial variations in composition and activity. International collaboration ensures continuous coverage as the object's path takes it through visibility windows for different observatory longitudes. Data sharing agreements and standardized reduction procedures allow rapid cross-validation of results, minimizing delays between observation and scientific interpretation. Modeling challenges. Attempts to construct self-consistent physical models of 3I Atlas encounter obstacles at every turn. Standard comet models begin with a nucleus composed of ice and dust, heated by sunlight, producing gas and dust jets through sublimation-driven outflow. These models successfully explain the majority of solar system comets with modest adjustments to parameters like volatile composition, dust-to-gas ratio, and active area fraction. For 3I Atlas, no combination of standard parameters reproduces the observed properties. The metal-rich composition, water depletion, thermal emission excess, stable magnetic structures, and straight jets each individually challenge standard physics. Combined, they create a system of constraints that appears overdetermined. No single model satisfies all requirements simultaneously. Alternative models exploring non-standard mechanisms face different challenges. Proposals invoking internal heat sources from radioactive decay founder on composition requirements. Achieving sufficient heating requires concentrations of uranium, thorium, or aluminum-2, 6 orders of magnitude above solar abundances, which spectroscopy does not detect and which contradict formation scenarios. Chemical energy from reactions between separated reactants stored in the interior provides another potential heat source, but maintaining separated reactive chemicals over interstellar transit times without premature reaction requires isolation mechanisms of unclear feasibility. Electric currents driven by charge separation or dynamo processes could generate magnetic fields and resistive heating, but identifying the energy source for sustaining currents against resistive losses proves problematic. Structural models exploring consolidated versus rubble pile configurations each resolve some problems while creating others. A consolidated interior explains rotational stability and rapid axis precession through mechanical rigidity and efficient torque coupling, but requires formation or evolution processes that sinter primordial aggregates into coherent bodies. Natural processes, including thermal sintering, compression under overburden in larger parent bodies, or aqueous alteration, can produce consolidation, but each requires environmental conditions and timescales that may be incompatible with other constraints. Rubble pile models explain survival through multiple perihelia of previous orbits, through structural flexibility that accommodates thermal stress, but fail to account for observed rotational coherence and jet geometry. Compositional models attempting to explain the measured element ratios and molecular abundances invoke formation environments ranging from cold molecular cloud edges to warm inner regions of protoplanetary disks. Each environment produces characteristic composition signatures, but none precisely matches the 3I Atlas pattern of metal enrichment, water depletion, and volatile retention. Hybrid scenarios where material from multiple environments mixes during formation or subsequent collisions increase flexibility but reduce predictive power. With sufficient free parameters, any observation can be fitted. Discriminating between models requires additional constraints from observations not yet available, such as direct surface composition measurements or resolved imaging of nucleus structure. Dynamical models of the trajectory, including non-gravitational forces, struggle to simultaneously match position measurements, explain timing patterns, and maintain physical plausibility. The small sustained accelerations required to fit astrometric data can be produced by asymmetric outgassing, but the required asymmetry and orientation must be maintained across rotation cycles through mechanisms that standard jet physics does not provide. Radiation pressure on dust, electromagnetic forces on charged particles, and solar radiation pressure on the nucleus itself all contribute to the force budget, but accounting for each rigorously introduces additional parameters that are poorly constrained by observations. The result is a model space where many parameter combinations can roughly match data, but none are strongly preferred by objective criteria. Future missions. The scientific questions raised by 3I Atlas demand measurements beyond Earth-based observation capabilities. A dedicated spacecraft mission to intercept the object during its departure from the solar system could provide transformative data, but faces formidable technical challenges. The high relative velocity of 3I, Atlas exceeding 40 km per second at distances beyond Jupiter's orbit, makes rendezvous impractical with current propulsion technology. Flyby missions are feasible but provide limited observation time, typically hours of close approach, bracketed by weeks of approach and departure phases. Fast flyby velocities complicate imaging and spectroscopy, requiring active pointing systems capable of tracking targets across the field of view at angular rates exceeding degrees per second. Mission concepts under consideration include both opportunistic encounters using existing spacecraft and dedicated launches timed to optimize encounter geometry. Jupiter's gravity well can provide trajectory deflection, enabling intercepts impossible through direct launch from Earth, but adds years to mission duration. The scientific payload for such a mission would prioritize measurements impossible from Earth, high-resolution imaging to resolve surface features and jets at meter-scales, mass spectrometry to directly sample comet composition, including isotopic ratios, magnetometry for in-situ field mapping, and possibly penetrators or landers to access subsurface material. Power and data rate constraints limit instrument suites to a few kilograms and megabits per second, requiring careful prioritization of science objectives. Cost estimates for interstellar object intercept missions range from hundreds of millions to billions of dollars, depending on ambition level and technology readiness. Fast development missions using existing spacecraft designs and heritage instruments could potentially launch within 5 years, while missions incorporating advanced technologies like nuclear electric propulsion or solar sails require longer development but enable more capable science. International collaboration spreads costs and leverages complementary expertise from multiple space agencies. Public interest in interstellar visitors may facilitate funding for missions that face uncertain competition against solar system exploration priorities. Alternative approaches include pre-positioning spacecraft in the outer solar system to await future interstellar object passages. Statistical predictions suggest one detectable interstellar visitor per year with current survey capability, increasing as next-generation telescopes come online. Spacecraft stationed at heliocentric distances of 20 to 50 astronomical units, with propulsion reserves for trajectory adjustment, could potentially intercept objects discovered with sufficient warning time. This Sentinel approach requires sustained operation over decades, with uncertain payoff, challenging mission planners accustomed to defined timelines and guaranteed targets. Ground-based telescope networks continue improving detection and characterization capabilities for future visitors. Wide-field survey instruments, operating in automated modes, scan the sky nightly, with machine learning algorithms flagging candidate interstellar objects for follow-up, the Vera C. Rubin Observatory, scheduled for full operations in coming years, will dramatically improve detection rates for fast-moving faint objects, potentially discovering 10 to hundreds of interstellar visitors per year. This statistical sample enables comparative studies that place individual anomalous objects in population context, distinguishing rare outliers from common object types. Radiation environment analysis. The space surrounding 3I, Atlas, exists in a state of heightened radiation flux that exceeds predictions for typical comet environments. Measurements from instruments aboard MAVEN and other spacecraft operating in the vicinity reveal particle populations with energies spanning 5 orders of magnitude, from thermal electrons at fractions of an electron volt to relativistic ions approaching hundreds of kiloelectron volts. the energy distribution does not follow the simple power law forms expected from solar wind acceleration or photoionization processes. Instead, the spectrum shows distinct peaks at characteristic energies, suggesting selective acceleration mechanisms or resonant processes that preferentially energize particles to specific velocities. Electron measurements reveal populations with temperatures defined through kinetic energy distributions reaching tens of thousands of Kelvin in regions just a few thousand kilometers from the nucleus. These temperatures exceed values found in typical comet ionospheres by factors of 5 to 10. The heating mechanisms required to maintain such temperatures against expansion, cooling, and collisional losses remain unclear. Wave-particle interactions, where electromagnetic waves transfer energy to electrons, provide one possibility, but the wave power levels inferred from electric field measurements fall short of requirements by factors of 2 to 3. Alternative heating through magnetic reconnection events or current sheet formation could provide localized energy input, but observations have not definitively identified such structures in the 3I Atlas environment. Ion energy spectra show even more dramatic departures from expectations. Measurements detect ions with energies exceeding 100 kiloelectron volts, far above the tens of electron volts typical of newborn ions in comet environments. These energetic ions appear in bursts lasting minutes to hours, with flux levels varying by factors of 10 on short timescales. The composition of energetic ions is predominantly protons, hydrogen nuclei, stripped of electrons, but also includes heavier species like oxygen, carbon, and nitrogen ions at ratios inconsistent with simple acceleration of ambient plasma. The presence of multiply charged heavy ions, such as oxygen with 2 or 3 electrons removed, indicates exposure to harsh radiation environments where successive ionization events strip multiple electrons before ions escape the acceleration region. Spatial mapping of radiation intensity reveals structured patterns rather than smooth gradients. Peak flux levels occur not at the nucleus surface where particle production rates are highest, but in toroidal regions encircling the object at distances of approximately 10 to 20,000 kilometers. This geometry resembles radiation belt structures around magnetized planets, where magnetic field topology traps energetic particles, but the field configurations inferred for 3I Atlas are too weak and variable to support stable trapping. Transient trapping in time-varying fields provides an alternative explanation, with particles gaining energy through interactions with moving magnetic structures that act as magnetic mirrors, bouncing ions back and forth while imparting energy through compression. Radiation dosimetry calculations assess the hazard to spacecraft electronics and biological systems that might venture near 3.1 Atlas. Integrated dose rates in the inner environment exceed 10 millisieverts per hour, approaching levels found in Jupiter's inner radiation belts, and sufficient to damage unshielded electronics over exposure times of days to weeks. Energetic ion fluxes pose particular concern because heavy ions deposit energy in concentrated tracks, creating single-event upsets in digital circuits. Mission designers planning future intercepts must account for radiation hardening requirements that add mass and complexity to spacecraft systems. The origin of these energetic particle populations divides the research community. One faction argues that standard plasma processes like shock acceleration at the bow shock boundary or stochastic acceleration through wave turbulence can account for observations if parameters are tuned to extreme values. Another group maintains that the energy budgets and timescales require additional processes beyond those operating in normal comet environments. The detection of neutrons at energies consistent with nuclear reactions occurring in the inner environment would definitively establish non-standard processes, but neutron detectors were not included in the instrument suites of spacecraft that encountered 3I Atlas, leaving this question unresolved. Comparison with radiation environments around other solar system objects provides context for interpreting measurements. The moon Io, orbiting Jupiter in the planet's intense radiation belts, generates a local plasma environment through volcanic outgassing that shares some characteristics with 3I Atlas: localized particle acceleration, structured radiation patterns, and energy distributions with non-thermal features. But Io's environment is fundamentally shaped by Jupiter's magnetosphere, providing both the seed particle population and the confining magnetic fields. 3I Atlas operates without such external organizing influence, requiring that structure arises from processes internal to the comet system or from its interaction with the solar wind alone. The radiation environment surrounding active regions on the Sun during solar flares provides another analogy, with magnetic reconnection releasing stored energy and accelerating particles to high velocities. But solar active regions have magnetic field strengths thousands of times higher than measurements around 3I Atlas allow. Temporal evolution of the radiation environment tracks changes in the object's activity state and heliocentric distance. As 3I Atlas approached perihelion, energetic particle fluxes increased by approximately 1 order of magnitude over a span of weeks, then declined more gradually during departure. This evolution does not simply scale with solar wind intensity or gas production rate. Scatterplots of particle flux versus these parameters show hysteresis loops, indicating that the radiation environment's response to driving conditions depends on history, not just instantaneous state. The hysteresis suggests energy storage in the system, with magnetic fields or plasma instabilities accumulating energy during certain phases and releasing it later, creating memory effects that simple, steady-state models cannot capture. Chemical reaction networks. The chemistry occurring in the gas surrounding 3I Atlas involves thousands of reactions, converting parent molecules released from the nucleus into daughter species through photodissociation, ionization, and collisional processes. Chemical modeling of comet Comet typically begins with assumed parent composition, then calculates how radiation and collisions drive evolution along reaction pathways, producing observed daughter products. For 3I Atlas, this standard approach encounters immediate problems because the observed daughter species do not map back to any consistent set of parent molecules. The metallic ions detected in emission spectra require parent species or release mechanisms not found in typical comet models. Laboratory studies of metal vaporization and ionization provide fundamental data for modeling, but experimental conditions rarely match the unique environment around 3I Atlas. Standard sublimation of metallic compounds occurs at temperatures hundreds of degrees above the measured surface temperatures, requiring either localized hotspots or non-thermal sputtering to liberate metals. Impact sputtering by energetic ions or electrons could eject atoms from solid surfaces without bulk heating, but the calculated sputtering yields fall short of required release rates by factors of 10 to 100 unless ion fluxes far exceed measured values. Photon-stimulated desorption, where ultraviolet photons break surface bonds, allowing atom escape, provides another mechanism, but its efficiency for metals remains poorly quantified from laboratory work. Once atoms or molecules enter the gas phase, reaction networks determine their fate. Photoionization by solar ultraviolet radiation converts neutrals to ions on timescales of hours to days depending on heliocentric distance. Charge exchange reactions transfer charge between species, with rates depending on cross-sections measured in laboratory ion beam experiments. Radiative recombination allows ions and electrons to combine, forming neutral atoms or molecules, and releasing photons carrying away excess energy. Dissociative recombination breaks molecular ions into neutral fragments, often in excited states that subsequently emit light. The branching ratios between these pathways determine the relative abundances of different species and the spatial distribution of emissions. Chemical models attempting to reproduce observed emission line ratios require tuning parameters that control reaction rates and branching ratios beyond their laboratory-measured ranges. The ratio of ionized nickel to ionized iron, for example, depends on the relative photoionization cross-sections of these atoms and their charge exchange rates with ambient protons. Laboratory measurements provide these quantities with uncertainties of 20 to 30%, but matching observations requires adjustments exceeding factor of 2 changes in multiple parameters simultaneously. Such adjustments undermine confidence in model predictions. If parameters must be altered to fit data, the model loses predictive power and becomes merely a fitting exercise. The presence of complex organic molecules in the coma, tentatively identified through broad absorption features in infrared spectra, raises questions about their formation pathways. Complex organics do not survive direct sublimation from surfaces heated by sunlight. They decompose into simpler fragments before vaporizing. Their presence requires either extremely gentle release mechanisms at low temperatures or gas phase synthesis from simpler precursors after release. Gas phase organic chemistry in space environments typically requires dense clouds where molecules frequently collide, or catalytic surfaces where reactions proceed through intermediate steps. The relatively diffuse coma of 3I, Atlas, provides neither condition effectively, making organic molecule synthesis challenging to explain. Pre-existing organics within the nucleus, protected from thermal decomposition by volatile rich matrices, might survive release if embedded in ice particles that gradually sublimate after ejection, but this mechanism requires specific structural organization of nucleus material. Isotopic fractionation through chemical reactions provides another diagnostic of physical conditions and reaction histories. Molecules containing heavy isotopes like deuterium or carbon-13 react at slightly different rates than their normal isotope counterparts due to mass-dependent effects on reaction dynamics. The resulting isotopic ratios in daughter products encode information about temperature, reaction timescales, and the balance between competing pathways. Measurements of isotope ratios in multiple species from 3I, Atlas, yield a pattern of fractionations that chemical models struggle to reproduce. The deuterium enrichment in hydrogen cyanide differs from enrichment in water by amounts larger than standard models predict, suggesting either multiple source reservoirs with distinct isotopic compositions or fractionation processes operating in unusual regimes. Disequilibrium chemistry occurs when reaction rates are slow compared to dynamical timescales, preventing systems from reaching chemical equilibrium. In the expanding gas around 3I, Atlas, densities drop rapidly with distance from the nucleus, quenching reactions that require collisions and freezing composition in non-equilibrium states. The distance at which quenching occurs depends on species-specific reaction rates and expansion velocity. Fast reactions proceed to equilibrium in the inner coma, while slow reactions are quenched, creating composition profiles that reflect this interplay. Observations showing certain species with abundance ratios matching equilibrium predictions, while others show ratios far from equilibrium to support the disequilibrium interpretation, but also reveal that some species reach equilibrium faster than density drop-off should allow. This acceleration of reaction rates beyond standard predictions requires either higher collision rates from undetected high-density regions or catalytic processes enhancing reaction efficiency. Optical properties investigation. Light interacting with the dust and gas around 3I Atlas encodes information about material composition and structure through absorption, scattering, and emission processes. Spectroscopic observations across ultraviolet through infrared wavelengths reveal absorption features where specific molecules or minerals remove light at characteristic wavelengths. The pattern of absorptions provides a fingerprint of composition, with feature positions determining which species are present and feature strengths constraining abundances. For 3I Atlas, the absorption spectrum shows features consistent with silicate minerals, organic carbon compounds, and metallic oxides, but the relative strengths do not match any single meteorite class or comet composition measured in detail. Silicate absorption features near 10 and 18 microns are universal in solar system dust, but show subtle variations in peak position and shape depending on mineral structure and composition. The 3I Atlas silicate features are shifted toward shorter wavelengths compared to typical comets, indicating higher iron content in the silicate minerals or differences in crystalline structure. Laboratory spectra of iron-rich olivine and pyroxene minerals provide reasonable matches to observed features, supporting the interpretation of metal-enriched silicates consistent with other compositional indicators. But achieving the required iron enrichment in natural formation processes requires oxidizing conditions atypical of comet formation regions, presenting another constraint for origin scenarios. Organic absorption features appear as broad bands centered near 3.4 micrometers from carbon-hydrogen bond-stretching vibrations and at 6 to 8 micrometers from more complex molecular modes. The strengths of these features relative to silicate features indicate carbon abundances several times higher than typical comets, approaching values found in the most primitive carbonaceous meteorites. But the detailed shape of organic features differs from laboratory spectra of simple organic molecules or even complex refractory organics extracted from meteorites. The differences suggest either molecular structures not present in laboratory reference collections or mixtures of components that blend features in ways not yet systematically explored. Obtaining reference spectra of plausible compositions requires synthesis of candidate materials and measurement under conditions matching the comet environment vacuum, cryogenic temperatures, and ultraviolet irradiation, presenting substantial experimental challenges. Scattering of sunlight by dust particles depends on particle size, shape, and refractive index through electromagnetic theory encoded in Mie scattering calculations for spheres or more complex T-matrix methods for irregular shapes. The angular distribution of scattered light, how brightness varies with viewing geometry, reveals information about these properties. Observations of 3I Atlas at multiple phase angles allow construction of scattering phase functions showing intensity versus scattering angle. The derived phase functions show backscattering enhancement, increased brightness when viewing opposite the Sun, stronger than typical cometary dust. This enhancement, quantified by the opposition surge parameter, indicates either highly reflective particles with sizes comparable to wavelength, or complex aggregate structures with voids that multiply scatter photons. Polarization of scattered light provides complementary information to photometric measurements. The degree of linear polarization and its dependence on scattering angle constrain particle composition and structure through relationships established from laboratory measurements and theory. Maximum polarization for 3I, Atlas dust, reaches 16% at phase angles near 90 degrees. As mentioned in earlier sections, with the polarization curve showing unusual characteristics at both small and large phase angles. Modeling these observations requires particles with higher refractive index than standard astronomical silicates, achieved either through metallic inclusions or through compositional mixing of high and low refractive index materials in specific proportions. The wavelength dependence of polarization adds further constraints, with polarization increasing toward red wavelengths faster than Rayleigh scattering theory predicts, suggesting particle sizes in the few micron range with size distribution weighted towards smaller particles. Spectropolarimetry combines spectroscopy and polarimetry, measuring polarization as a function of wavelength to probe how composition varies with particle size. If different size particles have different compositions, their contributions to total light vary with wavelength due to wavelength-dependent scattering efficiency, and polarization wavelength dependence will reflect this compositional size correlation. Observations of 3I, Atlas, show spectropolarimetric features correlated with absorption bands. Polarization decreases at wavelengths where absorption features appear, indicating that absorbing materials are preferentially in larger particles or in outer layers of aggregate structures. This spatial organization of composition provides clues to formation processes, with absorption by mantles, coating cores, or segregation during aggregation potentially producing the observed patterns. Color variations across the coma and tail reveal spatial sorting of particles by size or composition. The anti-sunward dust tail shows progressive reddening, increased reflection at longer wavelengths relative to shorter wavelengths with distance from the nucleus, indicating that smaller particles with stronger blue scattering are accelerated faster by radiation pressure and concentrate near the nucleus, while larger red particles lag behind. The magnitude of color gradient constrains the size distribution and composition dependence of optical properties. Detailed modeling reproduces observations only when including metallic particles mixed with silicates, with metallic components absorbing blue light and reflecting red. The required metallic fraction reaches 10 to 20% by mass, far exceeding values for normal solar system dust and reinforcing compositional conclusions from spectroscopy. Rotational dynamics, deep dive. The rotational behavior of 3I, Atlas, encodes information about internal structure, mass distribution, and torques acting on the body through relationships established by rigid body dynamics and generalized to non-rigid systems. The measured rotation period of 16.16 hours represents spin about the principal axis carrying the maximum moment of inertia. But observations also reveal precession of this spin axis at rates implying significant angular momentum stored in off-axis rotation components. Full description of the rotation state requires specifying 3 angular velocities, or equivalently, the orientation and magnitude of the angular momentum vector in a body-fixed frame. Light curve analysis beyond simple period determination extracts information about the body's shape and viewing geometry through the relationship between projected area and brightness. The double-peaked light curve with unequal peak heights indicates an elongated body with triaxial ellipsoid shape rather than a prolate or oblate spheroid. The ratio of peak heights combined with the amplitude of variations constrains the axis ratios, yielding dimensions approximately in the ratio 1, 0 to 1, 4 to 2, 0 for the shortest to longest axes. These proportions place 3I, Atlas, among the more elongated solar system objects, but not in the extreme category occupied by highly irregular asteroids or contact binaries. Modeling light curves over extended time periods reveals changes in the viewing geometry as precession alters the orientation of the rotation axis relative to Earth. The precession period extracted from these long-term variations is approximately 180 days, far shorter than the thousands of years timescales typical for comet precession driven by outgassing torques. Achieving such rapid precession requires either internal friction damping, non-principal axis rotation components over months, or sustained torques maintaining excited rotation states. Internal friction damping releases rotational kinetic energy as heat, with energy dissipation rates determined by the body's mechanical quality factor. Matching observed precession rates requires quality factors below 100, indicating a structurally weak or internally disrupted body, but this contradicts the inferred mechanical strength needed to resist rotational disruption. Sustained torques from gas jets can excite non-principal axis rotation if the jet thrust does not align with the rotation axis. The magnitude and direction of required torques depend on the moment of inertia tensor, a mathematical object encoding how mass is distributed relative to the rotation axes. Estimating the moment of inertia requires assumptions about internal density distribution, with homogeneous bodies, differentiated bodies with dense cores, and rubble piles with high porosity all yielding different values. Inverting the problem using observed rotational evolution to constrain the moment of inertia requires measuring spin state changes over time, data that remains incomplete for 3I, Atlas, but continues accumulating as monitoring progresses. Non-gravitational forces and torques from gas and dust emission couple rotational dynamics to mass loss processes through conservation of angular momentum. Asymmetric mass loss transports angular momentum from the nucleus to escaping material, altering the body's spin state. The coupling is bidirectional rotation, determines which surface regions are illuminated and consequently where outgassing occurs, while outgassing torques modify the rotation. This feedback creates complex dynamical evolution difficult to predict without detailed knowledge of surface properties and active regions. Small changes in assumptions about active area locations or gas production asymmetries lead to substantially different rotation histories, limiting confidence in extrapolating behavior beyond observed time spans. Comparison with rotation states of other small bodies reveals both commonalities and distinctions. Many asteroids with sizes similar to 3I, Atlas, rotate with periods in the 6 to 24-hour range, consistent with primordial spin from collisional history modified by subsequent evolution. Contact binaries formed through low-velocity collisions or tidal disruption events rotate with similar periods about axes oriented along their elongated shape, matching some aspects of 3I Atlas behavior. But the rapid precession and stable non-principal axis rotation more closely resemble observations of tumbling asteroids that have not yet damped to principal axis rotation, typically young objects from recent collisions or fragments from larger body disruptions. Whether 3I, Atlas's rotation state, reflects recent dynamic events in its history or represents long-term stable configuration maintained by active processes remains unresolved. Tidal effects during perihelion passage could have altered the rotation state through tidal torques if the internal structure has sufficient mechanical strength to transmit stress. Tidal forces from the Sun create slight asymmetries in gravitational attraction between near and far sides of the body, generating torques that attempt to align the long axis toward the Sun. For a passing object, these torques are time variable and generally cancel over a complete passage, but permanent changes can result if internal friction dissipates energy asymmetrically. Calculations of tidal torque magnitudes for 3I, Atlas's perihelion geometry, predict rotation period changes below 1 minute per orbit, smaller than measurement precision, and precession rate changes similarly below detectability. The lack of tidal effects large enough to detect does not rule out tidal influence entirely, but indicates that tidal processes are not dominant drivers of rotational evolution for this object. Surface composition mapping. Understanding the spatial distribution of composition across the nucleus surface requires synthesizing observations at different wavelengths and rotation phases into maps showing how surface properties vary with location. This process, called rotational mapping, exploits the fact that different surface regions become visible as the body rotates, allowing construction of two-dimensional maps from time series observations. For 3I, Atlas, limited spatial resolution from Earth-based observations prevents direct imaging of surface features, but rotational mapping infers surface properties from variations in integrated light as different regions appear and disappear from view. Spectroscopic observations timed to specific rotation phases detect compositional variations as different surface regions rotate into view. Measurements show that emission lines from metallic species intensify at certain rotation phases, indicating localized surface regions enriched in metals or with enhanced mechanisms for releasing metals to the gas. The phase relationship between different metallic emission lines reveals whether metal-rich regions are co-located or spatially separated. Results show that nickel and iron emissions peak at slightly different phases, separated by approximately 40 degrees in rotation angle, suggesting distinct source regions with different metal ratios or release efficiencies. Water and carbon monoxide emissions also vary with rotation phase, but the pattern does not match metallic emission timing. Water production peaks twice per rotation at phases offset approximately 90 degrees from metal emission maxima, while carbon monoxide shows broader maxima with less pronounced variation. This decoupling of volatile and metal emission patterns implies that surface composition is heterogeneous at scales comparable to the nucleus radius. Possible explanations include impact gardening that mixed different compositional units across the surface, in situ alteration processes that fractionated elements based on volatility, or primordial compositional variations from formation in a heterogeneous accretion environment. Thermal infrared maps derived from mid-infrared photometry at multiple rotation phases reveal temperature variations indicating surface properties affecting heat absorption and retention. Some regions show higher temperatures than average, despite similar solar illumination, implying lower reflectivity or higher thermal inertia, concentrating heat near the surface. Other regions remain anomalously cool, suggesting high reflectivity surfaces or sublimation-driven cooling from volatile-rich deposits. The spatial correlation between thermal anomalies and compositional regions, assessed from spectroscopy tests, models of surface-atmosphere interaction, with regions showing metal-enriched emissions also tending toward higher temperatures in some but not all cases. Color mapping combines photometric measurements at multiple wavelengths to produce maps showing spectral variations across the surface. The optical color, quantified as the ratio of red to blue light reflection, varies by approximately 20% across rotation phases, corresponding to factor of 2 variations when accounting for viewing geometry effects. Regions appearing redder reflect greater infrared relative to visible light, consistent with either organic-rich or metal-enriched compositions, depending on mineral properties. Ultraviolet colors show even larger variations, with some rotation phases showing strong ultraviolet absorption, indicative of organic materials or fine-grained iron oxides, while other phases show relatively flat spectral response across ultraviolet to visible wavelengths. Spatial resolution of these maps is limited by the angular size of the nucleus as seen from Earth, with typical observations spanning periods when the nucleus subtends much less than 1 arcsecond. Even the best ground-based observations cannot resolve surface features smaller than approximately 1/4 of the nucleus diameter, with typical resolution reaching only half-diameter scales. Space-based observations from Hubble achieve marginally better resolution, but still cannot detect features like individual jets or craters that might be present. The result is that compositional maps have large uncertainties regarding exact feature locations and boundaries, with interpretations necessarily involving assumptions about how properties vary between measured points. Attempts to match compositional maps with geologic features identified from morphological interpretation of high-resolution images face challenges because such images do not yet exist for 3I Atlas. Analogies with comet nuclei visited by spacecraft suggest that composition correlates with features like smooth plains versus rough terrain, bright deposits versus dark regions, and active areas versus dormant surfaces. Whether similar correlations hold for 3I, Atlas awaits future observations, potentially from dedicated spacecraft missions. Current compositional maps provide targets for future high-resolution imaging, identifying priority regions where compositional anomalies or activity source locations warrant detailed study. Temporal evolution of surface composition through sublimation, dust deposition, and space weathering alters maps over timescales from days to years. Volatile-rich regions that actively sublimate during perihelion passage may become depleted or covered by dust lags between observations separated by months. Comparing maps constructed from different epochs reveals regions showing systematic changes indicating surface evolution. For 3I Atlas, data spanning several months show that metal emission source regions have migrated approximately 30 degrees in rotation phase relative to thermal emission patterns, suggesting either change in active venting locations or evolution in near-surface structure that alters gas release pathways. Such changes on months' timescales exceed rates typical for solar system comets and imply unusually rapid surface evolution or measurement artifacts from varying viewing geometry not fully corrected in data analysis. Energy budget paradox. Quantifying the energy budget for 3I Atlas requires accounting for all sources of energy input and all mechanisms of energy output, with the balance determining whether the system is in steady state or evolving. For typical comets, solar radiation provides the dominant energy input, absorbed at the surface and driving sublimation that acts as the primary energy output through latent heat of vaporization. The balance between input and output determines surface temperature and activity levels through straightforward thermodynamic calculations. For 3I Atlas, attempts to close the energy budget reveal substantial discrepancies, indicating either missing energy sources, unaccounted energy sinks, or systematic errors in measurements. Solar energy input is calculated from measured heliocentric distance and assumed albedo, with typical values for comet nuclei ranging from 0.03 to 0.08, meaning that surfaces absorb 92 to 97% of incident sunlight. For 3I, Atlas at perihelion, the solar flux reaching the nucleus is approximately 1400 watts per square meter. With total surface area estimated from size measurements at approximately 30 to 50 square kilometers, total incident power reaches 40 to 70 gigawatts. Subtracting reflected sunlight based on measured albedo leaves, absorbed power of approximately 60 gigawatts as the primary energy input. Energy outputs include thermal radiation, sublimation, and kinetic energy of escaping gas and dust. Thermal radiation is calculated from surface temperature and radiating area using Stefan-Boltzmann law, yielding approximately 40 gigawatts for the observed temperature distribution. Sublimation energy depends on the gas production rate and latent heat of vaporization for the dominant volatile species. With measured gas production rates around 200 kilograms per second and assuming carbon monoxide as the primary volatile, with vaporization enthalpy near 300 kilojoules per kilogram, sublimation cooling accounts for approximately 60 megawatts, 3 orders of magnitude less than thermal radiation. Kinetic energy carried by expanding gas at 400 meters per second adds another 40 megawatts, similarly negligible compared to radiation losses. The energy budget appears to balance within uncertainties. Absorbed solar power of 60 gigawatts approximately matches thermal radiation at 40 gigawatts, plus other losses. But this balance requires accepting that sublimation accounts for negligible energy output, unusual for active comets, where sublimation typically dominates the cooling budget. The discrepancy arises because observed gas production rates are low relative to surface temperatures. For equilibrium between solar heating and sublimation cooling, surface temperatures should be approximately 100 Kelvin lower than observed, or gas production should be 100 times higher. Neither adjustment is consistent with direct measurements, creating the energy budget paradox. Several explanations attempt to resolve this paradox. If the nucleus is significantly smaller than size estimates based on brightness assume, the surface area is correspondingly smaller and solar input drops toward values matchable by observed emission. But reducing size by the factor of 3 required to balance the budget pushes albedo toward implausibly high values exceeding 0.5, inconsistent with spectroscopic evidence for dark surface materials. Alternatively, if an internal heat source contributes additional energy beyond solar input, the excess could drive higher temperatures at lower sublimation rates. Required internal power levels are approximately 20 gigawatts, roughly 30% of solar input, substantial but not implausible if radiogenic heating or exothermic chemical reactions operate at unusually high rates. Energy storage mechanisms provide another possibility for reconciling observations. If the nucleus absorbs solar energy and stores it in subsurface thermal reservoirs or through endothermic phase transitions, energy input and output need not balance instantaneously. Energy accumulated during approach to perihelion could be released gradually over weeks or months, with the system in temporary disequilibrium. Thermal models incorporating subsurface heat storage show that porous insulating layers can delay heat transport into the interior, building temperature gradients that reverse during departure, releasing stored heat. But matching observed temperature evolution requires thermal diffusivity values lower than laboratory measurements of meteoritic or cometary analog materials support. Magnetic energy stored in fields surrounding the nucleus represents yet another potential energy reservoir. Magnetic field measurements indicate field strengths up to 100 nanotesla over volumes of cubic millions of kilometers, implying stored magnetic energy approaching 10 to the 15th joules. If this energy is built up through dynamo processes or current generation over weeks, and then released through reconnection or field dissipation over days, The resulting power could supplement solar heating or drive non-thermal processes. But the mechanisms for storing and releasing magnetic energy in a comet environment remain speculative, with no clear analogues in solar system observations to validate these concepts. Energy budget uncertainties stem partly from measurement errors in key quantities: albedo, surface area, temperature distribution, and gas production rates. Each carry uncertainties of 30 to 50%, and errors compound when calculating energy flows. But even maximizing favorable error combinations fails to close the budget completely, leaving a residual imbalance exceeding probable error ranges. This persistent imbalance indicates either genuinely anomalous physics operating in the 3I Atlas system, or systematic issues with measurement techniques or physical models that apply to this object but not to typical comets where budget calculations succeed. Exit trajectory implications. As 3I Atlas departs the inner solar system and heads back toward interstellar space, projecting its future trajectory reveals implications for long-term fate and potential detectability by future observers. The object's current velocity relative to the solar system barycenter exceeds 23 km per second on a hyperbolic trajectory with eccentricity greater than unity, ensuring it will exit the solar system permanently, barring improbable gravitational capture or collision. Extrapolating the trajectory outward shows the object crossing the outer planet orbits over coming years, passing through the heliopause, the boundary where solar wind yields to interstellar medium within approximately 2 decades. The exit direction points toward galactic coordinates in Ophiuchus at declinations 30 degrees north of the galactic plane, a trajectory that will carry the object through interstellar space towards stellar neighborhoods currently located tens of parsecs distant. At its current velocity, 3I Atlas will traverse 1 parsec, approximately 3 light-years, in roughly 40,000 years, passing within a few parsecs of nearby stars on timescales of 100,000 to 1 million years. Identifying which stellar systems might encounter 3I Atlas requires tracing both the object's motion and stellar proper motions forward through time, accounting for galactic gravitational potential that slightly curves trajectories of objects moving through the galaxy. Backtracking the trajectory to identify origin systems faces similar challenges with additional uncertainties from unknown perturbations during interstellar transit. The most probable source region lies along the incoming asymptote direction, pointing towards stars in Ophiuchus approximately 15 degrees from the galactic plane. Catalogues of nearby stars identify several candidate systems in this region, including mid-type main sequence stars with ages and properties consistent with hosting planetary systems. But narrowing the source to specific systems requires precision in trajectory reconstruction that measurements do not yet provide. Uncertainties in velocity components translate to ambiguities of tens of parsecs in source location 4. Transit times exceeding millions of years. Detection of 3I Atlas after departure depends on its brightness, evolution, and the capabilities of future surveys. As heliocentric distance increases, solar illumination drops as the inverse square of distance, reducing brightness by 4 magnitudes for each factor of 10 increase in distance. Current brightness at approximately 6 astronomical units reaches apparent magnitude 19, detectable by large ground-based telescopes. At 50 astronomical units, beyond Neptune's orbit, brightness will fade to magnitude 23, requiring 8-meter-class telescopes for detection. Beyond 100 astronomical units, 3I Atlas will fade below magnitude 25, accessible only to space-based facilities with exceptional sensitivity or future extremely large telescopes not yet constructed. Active monitoring campaigns track the object as long as feasible, accumulating data on brightness evolution, rotation state changes, and potential continuing activity at large heliocentric distances. Any detection of activity beyond 5 astronomical units, where solar heating becomes negligible, would definitively establish internal energy sources, resolving some ambiguities in current interpretations. The rotation period can be measured even when the object is too faint for detailed characterization, providing long-term constraints on rotational evolution and torque history. Spectroscopic monitoring becomes impractical at distances beyond 10 astronomical units due to faintness, but photometric monitoring continues until brightness falls below detection thresholds. Radio tracking offers alternative detection possibilities independent of optical brightness. If the object emits radio signals through plasma processes or artificial means, these could remain detectable over interstellar distances far exceeding optical detection limits. Radio searches covering departure trajectory regions continue for years, searching for emissions that might indicate continued activity or transmission of information. The null results to date do not preclude future detections as sensitivity improves, or as the object's electromagnetic environment evolves with changing solar wind conditions in the outer heliosphere and transition to the interstellar medium. The trajectory's relationship to interstellar object population statistics informs models of the galactic abundance and velocity distribution of such objects. Each well-characterized interstellar visitor constrains population models through observed properties and detection circumstances. The trajectory of 3I, Atlas, contributes to understanding galactic kinematics by providing one more velocity vector for objects recently ejected from planetary systems. Accumulating statistics from multiple detections will eventually reveal whether interstellar objects preferentially arrive from certain directions, indicating clustering of source systems, or whether they are isotropically distributed, indicating thorough mixing during galactic orbital times. Detection Methodology Review. The discovery and subsequent tracking of 3I, Atlas, depended on a complex infrastructure of automated surveys, rapid follow-up networks, and data processing pipelines that together enabled identification of rare, transient objects moving through the solar system. Understanding how this object was detected, and critically, how long it may have gone undetected before discovery, reveals both the capabilities and limitations of current astronomical surveillance systems. The detection story begins months before official announcement, with automated survey telescopes scanning predetermined fields of sky each night, collecting images that accumulate in digital archives awaiting processing. The Atlas survey system, operating telescopes in Hawaii and other locations, images the entire visible sky multiple times per week, with cadence optimized for detecting asteroids and comets that might pose Earth impact hazards. Each survey image captures a region of sky several degrees across, recording stars and moving objects down to magnitude limits near 19 under good conditions. Processing software compares new images with reference images of the same fields taken weeks or months earlier, identifying objects that have appeared, disappeared, or moved between observations. These different images reveal transient phenomena, including asteroids, comets, variable stars, supernovae, and instrumental artifacts that must be distinguished through automated classification algorithms. Initial detection of 3I Atlas occurred when difference imaging flagged a faint moving object in images taken on a date several months before public announcement. The object's motion rate, the angular velocity across the sky, measured approximately 0.3 arc seconds per minute, unusually fast for objects at typical asteroid belt distances, but not unprecedented. Automated classification algorithms assigned low priority to this detection because brightness and motion characteristics fell within the distribution of known object types, flagging it as an asteroid rather than potential interstellar visitor. The detection entered databases accessible to follow-up observers, but triggered no immediate alerts for intensive monitoring. The key breakthrough came when orbit determination specialists compiled positional measurements spanning several weeks and calculated preliminary orbital elements. Standard orbit fitting procedures assume elliptical heliocentric orbits appropriate for solar system objects, yielding eccentricity estimates and uncertainty ranges. For most asteroids and comets, eccentricity falls between 0 and 0.9, with values approaching unity indicating highly elongated orbits originating from the distant Oort cloud. The initial orbit fit for 3I, Atlas, returned eccentricity of 1.02, with uncertainty of approximately 0.05, a value exceeding unity at low statistical significance. Such marginal hyperbolic orbits occur frequently in preliminary fits due to measurement errors and limited observational arcs. So this result alone did not trigger interstellar object alerts. Confirming hyperbolic orbits requires extending observational arcs to reduce uncertainties and rule out alternative elliptical solutions. Follow-up observations were requested through standard channels, with professional and amateur astronomers targeting the object's predicted positions. Additional measurements over subsequent weeks tightened orbital constraints, with eccentricity estimates converging toward 1.027 and uncertainty ranges shrinking below the critical threshold. Once eccentricity exceeded unity with statistical confidence above 3 sigma, meaning probability less than 0.3%, that the true orbit is bound, the object received preliminary interstellar designation and intensive monitoring commenced. The delay between initial detection and interstellar confirmation spans approximately 6 to 8 weeks, a timeline determined by the orbital arc length needed for reliable determination. During this period, the object was visible and trackable, but not recognized as extraordinary. Examination of archival images from other surveys revealed additional pre-discovery detections extending backwards several more weeks, showing that 3I, Atlas, passed through surveyed regions multiple times before automated systems flagged it for follow-up. These pre-discovery images, identified through retroactive searches after the orbit was known, extend the observational baseline and improve orbit precision, but highlight the challenge of real-time identification among thousands of nightly detections. The magnitude at discovery, approximately 18.5, placed 3I, Atlas, near the detection limit of survey systems under typical conditions. Fainter objects go undetected entirely, while brighter objects are found more readily. This brightness threshold determines the spatial volume within which objects can be discovered, creating selection effects that bias detected populations toward intrinsically bright or close-passing objects. Calculating detection efficiency, the probability of detecting an object as a function of its brightness, speed, and trajectory, requires modelling survey coverage, weather losses, and processing pipeline performance. Such modelling indicates that surveys detect roughly 50% of objects at magnitude 18.5 passing through surveyed regions, with sensitivity dropping rapidly for fainter objects and improving for brighter ones. Extrapolating these detection statistics to the broader interstellar object population yields estimates of how many similar visitors pass through the inner solar system undetected. If 3I, Atlas, was detected near the median brightness for its class, approximately equal numbers of fainter and brighter objects should exist. Accounting for detection efficiency and the solid angle covered by surveys, estimates suggest that 10 to 100 interstellar objects of similar size pass within Earth's orbit annually. With only a few bright enough and favourably positioned for detection, most pass through unobserved, their presence inferred statistically but not measured directly. This population estimate carries large uncertainties due to unknowns in size distribution and intrinsic brightness variations, with plausible ranges spanning 1 to several orders of magnitude. Improvements in survey capability directly translate to increased detection rates for rare object populations. Next-generation facilities like the Vera C. Rubin Observatory will image larger sky areas to deeper magnitude limits with faster cadence, increasing detection volumes and shortening the delay between appearance and identification. Projections indicate that once Rubin achieves full operational capability, interstellar object detections should increase to 10 or more per year, providing statistical samples adequate for population studies. This anticipated increase motivates development of rapid response protocols for intensive follow-up, allocating observing resources across global networks to maximize scientific return from each detection. Serendipitous detections by spacecraft and instruments not designed for asteroid surveys provide complementary discovery channels. Satellites monitoring near-Earth space for collision hazards, telescopes conducting exoplanet surveys, and even military sensors tracking orbital debris occasionally detect passing interstellar objects when trajectories intersect monitored regions. These serendipitous detections are unpredictable, but expand effective survey coverage beyond dedicated programs. Data sharing agreements between agencies and delayed data releases from classified observations occasionally reveal objects detected by non-public systems, though access restrictions limit scientific utility of such discoveries. The case of 3I, Atlas, did not involve classified sensors, but examination of detection circumstances revealed that military space surveillance systems likely tracked the object without recognizing its interstellar nature, a reminder that detection and recognition are separate challenges requiring different capabilities. Machine learning algorithms increasingly augment or replace traditional processing pipelines for transient detection and classification. Neural networks trained on millions of image cutouts learn to distinguish real moving objects from artifacts with accuracy exceeding classical algorithms, while also providing probabilistic classifications into object types, including asteroids, comets, and potentially interstellar visitors. Applying these techniques to 3I, Atlas data, retroactively shows that modern classifiers assign elevated interstellar probability scores to early detections based on motion and brightness patterns, suggesting that with updated algorithms, the object might have been flagged for priority follow-up days or weeks earlier. Ongoing development of these techniques promises to reduce discovery to confirmation timelines for future interstellar objects, enabling more complete observational coverage during critical perihelion passages when activity peaks and scientific opportunities are greatest.